Okay, so we're talking about derivatives today. And you guys, this will be your first, well, not really your first, but your second introduction to a calculus topic. I think you'll like derivatives a lot more, but let me go ahead and give you a disclaimer. What I'm showing you today is the definition of a derivative. To me, it's important that you know that, although you will see in your work in calculus, rarely, if ever, will you stumble upon this derivative, this definition. Because what I'm going to start showing you tomorrow is all these little tricks and shortcuts to taking a derivative of a function. But I want to talk about what a derivative is so you'll understand it. And just as a warning, if you get a wild hair and say, hey, I'm going to take Cal 1 in college, even though I passed the AP test, just to get an easy A, just know I ran into a student at Auburn once at a football game, Carlo Balon. I was talking to him and I said, how's school? He goes, well, you know I took Cal 1. I was like, why'd you do that? He made a 5. He goes, I wanted an easy A. He goes, do you know that our professor makes us do every single derivative using the definition of a derivative, which is what I'm going to show you today, which is no fun. I mean, it can take a 3-second problem and turn it into a 6-7 minute problem, and sometimes worse. So my advice to you is to learn your calculus next year really well, pass the AP test, get whatever you need to get credit in college, and then move on to Cal 2 if you need to take a Cal 2. All right? So anyway, we're going to talk about the definition of derivative. I have this great program. Let me see if actually it's come online. It's a Google application, and Google has had issues all day, and it won't let me use it. Oh. So something's going on here. It works on this one, but I can't hook that up because then I can't record. So anyway, I have fortunately a kind of an idea what's going to be happening here drawn out for you to visualize it. My program is really great. If it works tomorrow, I'll show you. So here's the bottom line of a derivative. Derivatives in calculus measure rates of change. Now, you right now are familiar with one kind of rate of change, which is what? Slope. And on a line, the slope never changes, right? So we can just look at an equation of a line, find the coefficient of the x, and go, hey, the rate at which this line is changing is 4 or 2/3 or whatever that coefficient happens to be. And since it always does that, it doesn't require any work. But what about a parabola? They also have slopes, but the slope's tougher to measure because the slope at any one spot, you'd almost have to draw a tangent line to it and then measure the slope of that tangent line. And then as soon as you move to a new point, what starts happening to those slopes? They're changing. So what we need to do in calculus, what we do in calculus is we're going to be measuring the rate of change of a function or the derivative of a function at any particular location. And unlike a line, which has a constant slope, the slope will be changing. So what we really do when we find a derivative is find a formula. So when you calculate a derivative, you're not going to always get an answer like -4, 2/3, or 1/2. You're going to get a formula like maybe 4x minus 3, or 2x squared plus 5, or any number of different things. And that formula is a formula you use to calculate slopes at different spots. And all you have to do is plug that point into your formula, and it spits out your derivative. But since it's changing, it'll give you a different derivative for each x value. Yes? I'll get it to you. Don't worry. Okay. All right. So, thank you. So what I want to show you is where this actual formula comes from. And again, tomorrow, we'll start up with all the rules. We'll start with the power rule, the product rule, the quotient rule. We'll get to natural log rules, all exponential rules. We'll go through all the rules of finding derivatives that are shortcuts that someone came up with that keep us from having to do this little process all the time. But here's what, and there were two guys that are credited with calculus. Isaac Newton was one of them. He was on one part of Europe or whatever, figuring it out. And then on a separate part was a guy named Leibniz. I forget his first name. But these two guys basically didn't even know that they were both inventing calculus until like years later, people went, oh, look, these published works of these guys were done at the same time. But it was essentially the same process. Now, we typically credit Isaac Newton for stuff like that here, but I think that Leibniz actually did a really great job in a lot of ways because the notations he used are really great, especially as integration becomes more difficult and we get into different kinds of integration, that involve more than one kind of variable. We call that implicit differentiation. When we get into that next year, You guys will get a taste of that in A, B, and BC. The Leibniz notation is really important, and I'll point out what that is here in a second. So, like, well, it's not the vertex, so it's not the bottom, because if it was at the bottom, the slope would be easy, right? It'd just be 0. But since it's not the vertex, it's a little over here on the side, it kind of looks like maybe there's a tangent line like this. Now, if you were able to come over here and say, all right, here's point P, I'm going to draw a tangent line in there. You were able to draw that tangent line, then you could literally take a ruler out and you could measure the rise over the run, right? And you could maybe figure the slope out. Problem is, I could have you walk up here and draw a tangent line that looks like that. I could have you walk up here and draw a tangent line that looks like that. And I could come up here and draw a tangent line that looks like that. And I doubt anybody would really be calling the other guy a terrible drawer, right? Because they all look kind of close, but they clearly, all three would have 3 different slopes. Maybe close, but not exact. So we wanted to be able to find an exact slope. So the way to find an exact slope is to use what Leibniz and Newton came up with. And that was to get really creative with the limit. So what they did is they said, okay, to find the slope of the tangent line that would occur there, which would be the slope at that x value. What they did is they started, which seems completely illogical, by drawing not a tangent line, but a secant line. And they said, hey, let's just draw a secant line in there, and we'll find the slope of the secant line instead. Well, obviously, that's a terrible idea if I stop right there, isn't it? Because clearly, that slope is not the same slope as the tangent line. But watch what they did. First thing they did was say, well, how do you find the slope of this secant line? So they said, well, we're going to let P be the point right here. And just to kind of give it a more formal name, we'll call this distance that I went over x. So that's moving over x. And then how much would I go up if I'm talking about the f function? Well, if I go over x, I would go up f of x. So the first point is x, comma, f of x. So there's my first point. And then he went and said, well, this next point was a little bit further over than x. In fact, that distance right here, I'm going to call it h. So the coordinate at q is not x f of x, it's what? How far did I go over? X plus h. And then how high did I go? F of x plus h. And then once I have 2 points, well, we already have an equation that does slope, right? Y minus y over x minus x. So here we go. Y, so my slope of my secant line would be this y minus the other y over this x minus the other x. And then when you cancel the x's out, you get this. Now, does this look familiar? You have been seeing this expression since Algebra 2, intentionally. Not just that maybe it's annoyingly too, but they've been throwing that out there. So at this point, you would go, oh yeah, we've been doing stuff like that. Well, this is the slope of the secant line. Now, the slope of the secant line, again, is not the slope of the tangent line. But what if I took this secant line right here, or this point Q right here? What if I took that point Q and I started bringing it down closer and closer to P? When I do that, what happens to the H value as the Q gets closer? It gets smaller. It gets smaller. And couldn't you say as H gets smaller, it approaches 0? So couldn't I say, hey, if H right here approaches 0, isn't that the same thing as saying, hey, the limit of this function as H goes to 0? Isn't that the same thing? And what happens as the H shrinks to nothing? The secant line becomes the what? Tangent line. So the fraction itself is the slope of the secant line. But when I take the limit of it as H goes to 0, the slope of the secant line becomes the slope of the tangent line, because when I get to 0, P and Q are in the same spot. Now, the problem with that limit is what? What happens is you go to evaluate. You plug 0 in for what? H, and what do you get? You're going to get 0 on top and 0 on the bottom, which means there's a hole. And the upside of that is, what happens when we get holes?
We know
there's a limit at holes. So I know there's a limit here, which means I know there's a derivative. Now, the math on this is ugly, because normally when we get 0 over 0, what do?
Factor.
We factor, and then we cancel junk out, right? And then we redo the limit. Problem is, this doesn't factor right now. So what I'm going to have to do is literally evaluate this crap function right here, f of x plus h minus fx over h, clean it as much up as I can, and then cancel anything that possibly cancels, and then redo the limit. And that process is very tedious and not very fun. And I'm going to show it to you. We're going to do a couple, but I'm hoping that you will learn today and other days how to avoid having to do this ever again in my class or AP Cal, because there's ways around it. One of them is called L'Hopital's rule, which once you learn how to take a derivative of things, you'll be able to apply that, which also means when you go back and start doing limits, anytime you get a 0 over a 0, you'll be able to apply this L'Hopital's rule. And you won't have to memorize all that crap. Like, remember that function, 1 minus cosine x over x? It's equal to 0, and we're like, we don't know why, other than when we graph it, we can see the thing go to 0. Well, L'Hopital's rule answers that really easily. Or those trig functions like tan of 4x over sine of 3x is 4/3. Why? You got to memorize those rules. Well, you know L'Hopital's rule, and you can apply L'Hopital's rule anytime you get a 0 over 0. And there's another way I'll show you how to get around it too at the end of the day. So this is kind of a demonstration of why this rule works and why this expression is a definition of a derivative. And there's another one too, but this is the primary one that AP Cal uses. So I wanted to show you that. There's another one that I have written out later on. It finds a derivative, but it doesn't give you a formula. It finds actual numerical derivative out of spot. It doesn't give you a formula to find other things. So this right here, again, the limit of that secant line, which is this thing. The limit as h goes to 0. That whole result, that is the slope of the tangent line, and that is what we call the derivative. Okay? So let me show you a couple other things, and then we'll practice these. A couple other things is how I'm going to ask you this. If I want you to take a derivative, there's a lot of ways I can ask you. One is I can say, hey, can you find the slope of the line that is tangent to the curve at that particular x-side? Well, literally, that is the definition of a derivative. It's the slope of the line that's tangent to a curve at an x-side. So if you see this expression, you go, oh, take a derivative of the function. I can also say, hey, what's the instantaneous rate of change? Rate of change means slope. So instant slope means what is the slope at a particular instant on a curve? Well, the slope of that is the slope of the line tangent to a curve. Again, asking you to take a derivative. Sometimes I'll say, hey, differentiate the function. Differentiate isn't like a real world where you're trying to tell the difference between one thing and another. You're literally taking the derivative. And finally, the most frequent thing is when I give you a function like fx, I'll say do f prime of x. That's how you read it, f prime of x. Or if I give you something like y, I'll say find y prime. That's another way of saying taking the derivative. And then the Leibniz notation, that's what this is. This is the Leibniz notation. He's saying take the derivative of y with respect to the x-axis. And what's great about this notation is we aren't always dealing with an x-axis. Who's taking physics right now?
Man, this whole class was a chemistry class.
Well, that must have been a separation. Okay, so in physics, a lot of times you're dealing with position. And you're talking about the position at any moment in time. When I take a derivative, well, I'm not taking a derivative with respect to the x-axis. I'm taking a derivative with respect to the t-axis. So I would do dy dt. Or if how many gallons per minute? Say something was pouring into a container. Well, the x-axis might be the minute axis, right? It could be time or whatever. So sometimes the x-axis changes and it represents something else. So instead of taking the derivative of the y with respect to x, I'll go dy dt. I might go dv dt. So this notation is much better. But for now, we're going to be dealing with functions all the time. And functions, you're going to see a lot of f prime, y prime, or dy dx. And we read that dy dx, not dy divided by dx, it's just dy dx. And another thing we could say is, in case I didn't write it as y equals, if I wrote it as fx equals, sometimes you'll see dfx dx. Or if I wrote it as, or you could write ddx function, or ddx that. But ddx that, or ddx that, or ddx that is the same thing as ddx that. It's just another way of saying the derivative. And believe me, you'll get used to it and it will not be a big deal. My calculus and my pre-calc students never think twice about this. Now, a couple other things. There is something called a second derivative, and it measures something. It tells you about things like, if I found out that the derivative was positive, what do you know about positive slopes? There's a positive slope, the graph must be moving kind of upwards, right? Increasing. If you got a negative slope somewhere, means the graph is moving downward. That's a first derivative. So a negative first derivative, you can go, oh, the graph must be decreasing there because the slope's negative. If you got a 0 for the first derivative, oh, it must be at a min maybe, or maybe at a max maybe, or maybe it's kind of flattening out for a second and then dropping some more. But things that we can find. Second derivative doesn't measure that. Second derivative measures concavity. It doesn't really measure, indicates it. So like if you did the second derivative and got a plus, we'll talk more about this much later. Concave up means it's kind of cupped. Concave up is kind of cupped. Concave down, like a frown, people say, I guess. Anyway, so if you took the second derivative and got a positive, that would be like a parabola moving upward like this. Or maybe if it was an x cubed function, it's the cupped upward part. But if you took the second derivative and got a negative there, that means it would be cupped downward there somehow. But this notation shows second derivative, third derivative. And if you're wondering, well, that's weird. Why is the 2 on the d and then the 2 on the dx or on the x? Why isn't, if you're taking the second derivative twice, why isn't it d2y d2x? Well, here's the reason. If I have a function, to take a derivative, you ddx it. To take a second derivative, you ddx it again. So what you really see here is d squared y and dx squared. But nobody writes it as dx squared. They write dx squared. And it looks like you're squaring the x, but you're really not. But again, it's a notation that you'll get more comfortable with. You rarely will have to write it because most of the time it will be written for you and there'll be little equals out there and you'll be calculating it. And all you got to do on the second derivative is take the derivative twice. Take the derivative, get a function, then take the derivative of your new function, get another function. So all of this will not be a big deal, but I just wanted you to know different notations for things. And I don't know, I can't even think of when I've done a third derivative or where I've seen that on an AP test. So let's get back to actually doing one of these. So here we go. Find the slope of a line, the slope of the line that's tangent to that function at any particular x value. So what does that mean when I say find the slope of a line? Take the derivative. So since I started with f prime, what I would normally do is go, all right, since I started with f, I would normally say, hey, f prime of x is. Now, I'm going to show you tricks for all this, so you're not going to have to do this, okay? What you're going to learn tomorrow is you're going to look up here and go, wait, if that's the function, the derivative is 6x minus 2. Just remember that. That's how easy it will be for you to take a derivative of something like this tomorrow. But I want you to see the y of it. So what I would have to do using the definition of a derivative is go, well, if I'm going to take the limit of this function, I got to figure out what that is first. Well, what is f of something? Plug the something in. So I plug the x plus h there and there in my function, and I'm going to bring all of this and replace that with it. And you can see that I did that right here. And the second part says subtract your function. Well, I already have that. The function was the original problem. So I'm going to subtract the entire function right there. And be really careful that when you do that, you put parentheses or distribute the negative. If you forget to distribute the negative, there will be a way you can catch your error, but it's probably the number one thing I see people mess this up. They forget to distribute the negative. And then all you got to do next is, again, subtract them and divide by the h, and you're going to clean this up. Now, right there, if you're thinking right now, Well, why don't you plug 0 in? It's a limit, man. That's what you told us to do all the time, plug a 0 in. Well, I know that when I plug a 0 in, I'm going to get 0 over 0. That's what happens on these. You can see it right here. Plug a 0 in for h, and what do I get? 3x squared minus 2x plus 1 minus 3x squared minus 2x plus 1, 0 over 0. So what I'm going to do is foil the crud out of all this, clean it all up, and I bet I'm going to see the factorable, the thing that's going to cancel. Like I can tell right now what I'm supposed to cancel. I got an h, is the only thing on the bottom, right? That's what's giving me the 0. So all of this on the top and the bottom have a common h. I just can't see it now. But check it out. Square this. Here we go. All right, and now distribute the 3 in, distribute the negative 2 in, distribute that negative in. So I'm distributing everything in once I square that value. That gets me to here. Now, if you've done it right at this point, this will always happen. Everything in your f of x, if you've distributed the negative, everything should cancel. Check it out. Negative 3x squared, positive 3x squared, positive 2x, negative 2x, negative 1, positive 1. And everything you have left, if you notice, has an h in it. And if it has an h in it, what can you do? Cancel one of the h's out of each part, which now leaves you this. Now you do the limit by plugging the 0 in for h, and you're left with 6x minus 2, which would be my derivative of my function, which we already knew was going to be 6x minus 2, and you will tomorrow once you learn the rules of taking a derivative. You with me so far? Now, that looks like a formula, right? So on this particular function, which you can tell is a parabola, what if I said, hey, tell me what the derivative is, Thomas, when x is 2? Well, you would look down there and go, oh, well, if this is the derivative when x is 2 would be 10. Well, that's right. The slope at x equals 2 is really steep there because this graph is doing this. What about the derivative at negative 2? We plug in negative 2 right there, and you get a slope's negative 14. Because at negative 2, it's also steep over there. But what if I said, hey, what's the derivative at 1/3? X equals 1/3. You plug a 1/3 in there, and you get 2 minus 2 is 0. So that must be where the slope is 0. What would that mean?
That's the minimum value.
Which would mean it was the what? No, the minimum value would occur there, but that would be the x value of the what? Of the vertex. And by the way, if you know the x value of the vertex is at 1/3, you could have done negative b, right? Remember the little trick? Negative b over twice a, and you could have gotten 1/3 using our little trick for finding the vertex. But calculus allows you to find those mins, the places where the mins occur or where the slopes are 0, much easier than memorizing a little formula, because our formula only works with parabolas. It doesn't work with anything else, or the 3 problems that were on your test that required you to find minimum values, which were not fun if you didn't know calculus. Actually, there's a trick on one of them you could have learned, but you would have had to been deep in the math team Bible to see that one. Bless you. Are you seeing this? So let me do one more, and then I want to show you a way I'm hoping you avoid ever having to do this on the AP test, because I'll show you what AP is going to do. Okay, so on the next page, 61, I have 3 problems. I'm hoping you'll do number 1 and number 2, but I'll do the hardest one, number 3, because it involved a cubic. So I'm going to come down here to number 3. So the question was, find the derivative. So if this is my function, then the derivative of f I could find by pulling out my limit. So the limit as the h shrinks to nothing of what? What do I need in this fraction? What's the formula? I need the f of x plus h, right? So I got to take the x plus h, plug it there and there, and bring that down. So here we go. Here's the x plus h cubed minus the 3 times the x plus h plus the 1. So there's my first part. Now what do I do once I do the f of x plus h? I subtract f of x. Well, f of x is just the original problem. So I'm going to subtract the original problem. And then my rule is f of x plus h minus f of x over h. So all I have to do is do this limit now. And again, what's going to happen if I try to do the limit right now and I plug in 0?
0.
I get 0 over 0. So I know that I got to cancel something to get rid of that 0, 0. And since that's the only thing on the bottom, it's going to be an h. But I can't cancel an h right now because not everything has an h. So I got to FOIL all this thing out, clean it all up, and then I bet there'll be nothing but h's. Now, I don't want to FOIL this out and then FOIL it again, right? So I'm going to pull out Pascal's triangle. Do you remember what to do when it's cubed? I won't ask you this on a test if you're thinking that. Yeah, I go to the 1, 3, 3, 1, 1, 3, 3, 1. Then I start with x and go down, and then I go over here and start with h on the right and go down. And if it's plus, I don't alternate, I do all pluses. So that is this. I'm going to distribute that 3, that negative 3 in. I'm going to do plus 1, and I'm going to distribute that negative in. And again, I'm not going to ask you to cube anything on this test, but even if I did, you're going to have a backdoor, a better way to do it than this. All right, bring over the h, bring down the limit. Now, what did I say should happen if you've done it correctly?
All but the h's should cancel.
Everything over here on the right, the f of x should cancel, leaving you nothing but terms with h's in them. And sure enough, look, negative x cubed, positive x cubed, positive 3x, negative 3x, negative 1, positive 1, and then sure enough, I've got a 3x squared h plus a 3x h squared plus an h cubed minus a 3h over an h, and you can clearly see, I think, to me it's clearly, that everything has an h, and that's what's giving you the 0 over 0. So if you want, you can factor the h out and cancel it, or you can do like I'm about to do, which is cancel a single h out of each part, and then redo the limit, which gives you 3x squared plus 3xh plus h squared minus 3. And now when you plug a 0 in, those go away, and you get 3x squared minus 3. And you will find tomorrow that when you do the power rule right here, you'll literally look up here and go, oh, 3x squared minus 3 plus nothing, and you'll be done with that derivative. But once you learn the power rule, that won't be a big deal. All right? So see if you can do 1 and 2, but before you look at those, I want to talk about this next part. So let me show you what AP does. Everybody have this that wants it? I'm recording it if you want to go back and look at it. You got it? Okay, so let me show you what AP does. And again, once you learn a derivative, you'll have 2 ways to do this. And gotta be honest with you, most people don't do it the way I do it. My students that really are on their game, like that really know stuff, which honestly is you guys, if you really are on your game, because I have students that come from the regular pre-cal, sometimes they're great, sometimes they're average, whatever. And sometimes my pre-cal kids that come up are lazy. So, and they get to this point and they don't remember stuff because they've been just on cruise control. But what AP does is they don't tell you any of this junk. Like right here, let me just show you this and then I'll go backwards. If this was my function, does it make sense that this would be my derivative? There is my x plus h cubed right there. There's my x cubed right there. I'm subtracting, dividing by h, taking the limit. Does it make sense that on this one, here is my 3x plus h squared minus 2x plus h. That's that part. Here's my f of x being subtracted, divided by h, there's the limit. Do you see this happening on all these? Here is my natural log of x plus h right here. Here's my natural log of x. I'm subtracting, dividing by h, there's my limit. Okay, here's what AP does. AP, they don't even tell you f prime. They just give you this. So they don't tell you anything. Nothing. You just see this picture. And you have 2 things that you could do here. One, you could look at it and go, oh, another limit problem. And that's okay. If you see a limit problem, you'll be able to do L'Hopital's rule. Although L'Hopital's rule is a little tricky, when you're taking a limit as h goes to 0 and you have x's and h. Some people get lost in it. But what I'm hoping you do this, I hope you look at it and go, wait a minute. I recognize this h to 0 h and this x plus h junk. This is a definition of a derivative. This is the definition of a derivative of some function. So if I could only find that function, what function got x plus h plugged into it? Can you tell?
Cosine squared.
Cosine squared of x, right? So if that's my function right here, instead of doing the limit definition of a derivative or doing that limit, if I recognize that that's a derivative, I could pull out my derivative rules and just take the derivative of this function. Now, you don't know that right now, but it will be child's play for you on this test for you to go 2 cosine x times negative sine x. And that will not be a big deal for you once you learn how to take a derivative of a trig function. That is what I get if I were to do this ugly thing. But believe me, you don't want any part of doing this ugly limit. You'll also want a process called L'Hopital's rule. You could be able to do this one. All right, come down here to number 2. Again, number 2 says, all right, what if you were given this? And again, AP would not tell you it's the derivative. They just give you this. And they say simplify. And you don't even know anything about all this. They're just giving you this. And they say simplify. My hope is, next May, that when you see this, you go, oh, wait a minute, that's a limit. Look at this h to 0, h, x plus h. What function did x plus h get plugged into? Don't even bother. Do it this. What did it get plugged into? 3. Oh, that's a 3 times. Sorry, yeah. So 3 root x. Does it look like root x? I mean, x plus h got plugged in there to give you that part? Y'all see it? And for those of you who are just looking at this, there's a reason why I'm not doing that. I'll show you in a second. Well, if that's my function, and this means definition of a derivative, I can just take the derivative of that. Now, again, you're going to learn this tomorrow, but the shortcut for doing that is this. And you'll learn that tomorrow. Let me jump down to something a little bit more tricky. And this is why. I'll do these last 2. And it's not super tricky, but just look at it. Number 3. They're going to give you this limit. And some people look at it and they go, oh man, another crappy limit I got to do. Heck. Another crappy limit. But hopefully some of you will go, wait a minute. H to 0, h, x plus h. This is a definition of a derivative of some function. Maybe if I just found the function, I could take the derivative of it. Can you tell what x plus h got plugged into? Can you see that? Well, if that's my function, you'll learn first thing tomorrow that the derivative of that function is 5x to the 4th plus 2x to the 1st. And you'll be done. And if I did this the hard way, which good night, man. You want to go to Pascal's triangle to the 5 row? What is that? 1, 5, 10, 10, 5, 1. Expand that sucker, square that, distribute that, cancel the crud out of everything. I don't. But if you did, you end up with that. But man, this just seems like a lot easier to figure out the function and take the derivative using your derivative rules. Now, you don't know those derivative rules right now. So anyway, I'll come back to this a little bit. But the reason why I'm not looking at this stuff on the right is, look, here a lot of people accidentally say, oh yeah, my function is x to the 5th minus x squared. Do you see their mistake? The negative got multiplied in, didn't it? If I rewrote it by factoring that negative back out, I would see that it's really plus there. So people make mistakes looking at that, or even worse mistakes. Look down here at number 5. On number 5, and I got to be honest with you, a lot of times on number 5, they don't even write it like this to kind of make it look like it's happened. They just write 10, because that's what t cubed plus 2 is. But I could still look at this and go, wait a minute, it looks like an x plus h got plugged in. Now, x is 2, which is another thing we'll talk about in a couple seconds. But if the x plus h got plugged in here, what function did x plus h get plugged into? Can you see it? What is it? X cubed plus an x. That's what x plus h got plugged into. So what you'll do then is you'll look at this and you'll take the derivative, which tomorrow you'll learn is 3x squared plus 1. And then you're going to do one more thing. This actually told you that x was 2. So you'll take one more step and plug the 2 in and get the actual slope when x is 2. So those are all tips to why you can avoid. I just basically found the derivative, which you will be able to do tomorrow. I found the derivative not having to simplify any of this trick stuff. I mean, any of the whole thing out. But I would rather not. So I'm going to use some of those shortcuts. And we'll go back through this again. It'll be again on some homework problems or on your review to give you another reminder about that. But tonight, you don't have to do any of those derivatives. If you can just do those 2 problems and then just make sure you're here tomorrow, or if you're not here tomorrow, really make sure that you know your derivative. I mean, that you 7, 8, 9, 10, 8.
The 1 and 2 on this one. Look at these.
Yes. Really make sure that you are watching the video if you're not here tomorrow, because we're going to go over a ton of rules in the next 2 days. All right? In fact, it doesn't even say you have homework tonight. So, but I did want you to finish up those 2 problems just to give yourself a little bit of practice. All right? All right.